Are we going to do a special start for this one, Matt? Is there a joke you want to tell?
Have we actually started?
I don't know. Have we? Welcome, everybody, to another episode of Dr. Matt and Dr. Mike's Medical Podcast. Oh, no, I meant to do this one. All right, we've got a new interface that we're playing around with, as you can probably tell. Matt doesn't have headphones on, so he has no idea what sound I pressed.
What were they? A cheering and a...
Wah, wah, wah.
That's suitable for you.
Thank you. Matt, what are we talking about today?
I believe it's antibiotics.
Oh, how many antibiotics are there?
Well, categories?
Types.
Like actual individual antibiotics?
Yeah. How many do you reckon?
Hundreds.
Yeah, there would be a lot. We're going to go through today. I'll give a brief overview. We're going to discuss the difference between human and bacterial cells. We're going to explain basically how we can exploit these differences through antibiotics.
Okay.
We're then going to discuss different antibiotic classes, and you're going to give us a brief history on some of the types of antibiotics. And then we're going to talk a little bit about antibiotic resistance. What do you think?
Sounds like a lot, but
Yeah.
I'm glad you gave us a good signpost to begin with.
Thanks. All right. So, firstly, bacterial cells. What's so special about them?
I never said there was.
Oh, okay. So we don't have cells that look like bacterial cells.
So you mean human cells?
Yeah, we being human beings.
Okay.
Well, okay, probably if I were to take every human cell from your body and put it aside, I'd be able to find at least one or two bacterial cells to match it. So for every one of your cells, there's at least 1 to 2 bacterial cells. It's not 10 to 1 like they used to think, but more like 2 to 1.
Oh, 2 to 1.
Yeah, 2 to 1 to 1 to 1. So there's a lot of bacteria. So, you know, depending on the way you think about it, we could be seen as vehicles for bacteria.
Right.
Maybe.
All right. And when we are comparing this to our cells, we're referring to eukaryotic cells.
Yeah, eukaryote.
And bacteria cells being prokaryotic.
Yeah, eukaryote meaning true nut and prokaryotic meaning before nut. And the
so
nut
the
refers
carrier
to a
is
nucleus.
nut. I thought carrier was like chromosome. Or
Nut. Means nut. Yeah.
So when you do a carrier type in, that's...
You're looking at what's in
nuts.
the nucleus.
Okay.
Yeah.
Right.
That's what it's referring to. So that's the first big identifier between our cells and bacterial cells, or eukaryotes and prokaryotes, is that we have a true nucleus.
Bacteria don't have nuts.
They don't have nuts.
Oh, that's good to know.
So similar to you.
How do they reproduce then?
Binary fission. And we'll talk about that in a sec.
So romantic.
So we have a nucleus, and inside that nucleus, we have our DNA. So prokaryotes, like bacteria, they don't have a true nucleus, which means their DNA are free floating. So that's one big difference.
Okay, so the first difference is bacteria have freely floating DNA.
Yes.
Is it DNA or RNA?
DNA.
Okay. All right. And how is it floating? Is it in a...
How's it packaged?
Yes.
Because ours are packaged in chromosomes. Theirs are not packaged in chromosomes. They've got what we call plasmids. So so we have linear DNA. So it's one big long stretch like a ladder wrapped in around
a rope
itself.
ladder?
Like a rope ladder. That's good. But bacteria have circular DNA, but it's still a double helix. So it's still 2 strands wrapped around each other.
Okay.
But it's circular.
Right. So it still has its compaction like we do, but it just doesn't compact it into chromosomes.
That's right.
Okay. All right. So
just tight little plasmid.
So first difference is the way that it stores its DNA is different.
Yep.
Okay. Next.
So the shape was different. We stated that. Next one is that...
What do you mean the shape's different?
Well, there's circular DNA, not linear DNA.
Yes. I thought you meant the shape of the cell.
Oh, sorry. Okay. So the next one would be if we keep looking at the DNA, the way that the DNA unwinds to make more DNA.
Okay.
The chemicals that we use called topoisomerase, which unwinds the DNA, bacteria use a different type of topoisomerase.
Okay, so both types has a double-stranded DNA that's wrapped on itself. That's not different. The only difference is we package our DNA into chromosomes, so 23 pairs. Theirs is in plasmids, so circles. Now, the way that it's then packaged differently, they have enzymes different to ours to do that packaging, and that's
to unravel it.
Or unravel it. Okay, so what's that called?
Topoisomerases.
And so going back to my days of in undergrad doing my genetics, I recall something called a gyrase.
Yep.
Is that one of them?
Yep.
So that
topoisomerase 4 and gyrase are two really important molecules that help unwrap DNA so that it can be read to make more DNA.
Okay, so it pulls it apart so you can read the alphabet, the DNA alphabet.
Yeah, I think our listeners are smart enough to know the words nucleotides.
Okay, all right.
A, C, Gs, and Ts, which are the same between bacteria and humans. It's actually universal between all organisms.
Okay, so that's two differences.
Yep, another difference is that when they take the DNA, the way they turn the DNA into RNA is different. Transcription. That's right. So by something called RNA polymerase, we use different types of RNA polymerase to bacteria.
Right, and so that's another difference.
Another difference. Want to know another difference on top of that?
Sure.
Okay. So when we take that RNA and translate it into proteins, we use something called ribosomes. Now, humans have a 40S and a 60S ribosome subunits.
So this just means the ribosome, which are like little men inside your cells that help.
Whoa. I've got little men inside of my cells.
Yep. These particular little men grab the RNA. So we've already done the transcribing from DNA to RNA. So we've scribed it out, copied it.
Yep.
Now
other synonyms.
Now we're translating it. So we're changing the language from the RNA language into protein language.
Yeah, into amino acids.
And the thing that does that are ribosomes.
That's right.
And so
one of the things that helps that is ribosomes.
For humans, we have a ribosome that has a 40 and a 60 part to it. So it's kind of got like two parts to each ribosome. A 40 and a 60.
Yeah, 40S and 60S.
Okay, whereas a bacteria has a 30 and a 50S.
That's right. Do you know what the S stands for?
No.
Seconds. Because if you take those subunits and spin them in a centrifuge, that's how long it takes for them to become...
to drop to the bottom.
Yeah.
Oh, that's awesome.
And when you put them together, they make...
Wouldn't it matter? It wouldn't determine how quick you spin it though?
No. Well, yes, it's... yeah, of course.
So that's at a particular speed.
It is. It's at a particular G, gravity. I'm not sure what that is. But anyway, they're the differences. So ribosomes, like you said, have a 30S and a 50S. We have a 40S and a 60S. So again, more differences. And again, the whole reason why we're highlighting these differences is so we can exploit them with the antibiotics we bring up shortly.
Okay, any more?
Yeah, there's heaps more. Oh. So if we move away from DNA for a little bit, what if we look at the morphology of the cell?
The way it looks?
The way it looks and the way it's structured.
Okay.
So what are our cells surrounded by?
Membranes.
Okay, and what are those membranes made of? Well, what is that? Let's just take a single cell from our body. Yeah. What is that membrane made up of?
Phospholipid.
Okay, is there one phospholipid layer or two?
It's a bilayer.
Okay, so we have a phospholipid bilayer. That took a while to get out of him. So we have a phospholipid bilayer. Do bacteria have phospholipid bilayers?
Yes.
Okay, how many?
There are two types of bacteria.
Okay.
There's a gram-positive and gram-negative.
Yep.
So I think gram-negative have two membranes and gram-positive only have one.
Okay, very good. Okay, Matt passed that.
Yes.
So they have membranes, but there's differences in those membranes between us and theirs. So for example, embedded in our membranes, we have sterols. And these sterols in our membranes help maintain the rigidity and integrity of our membranes so they don't fall apart.
So this is like cholesterol?
Like cholesterol. Bacteria doesn't have it. So they've got pretty flimsy, crappy membranes.
Okay.
But like you said,
Insult into the bacteria.
they're pathetic. They're pathetic, and come at me. They've got.
You're outnumbered 2-1, so be careful what you say.
That's a good point, actually.
You could probably get diarrhea this afternoon now.
Not probably. All right, so cell walls is something that bacteria have that we don't, and this is what maintains the structural integrity for bacteria. So
why? Why do they need that?
well, they need it because they've got such pathetic cell membranes that aren't very strong, and inside of a bacteria, it's hyperosmotic.
All right, this is what I was getting at, yeah. So they need extra support, otherwise they explode?
That's right. So they're hyperosmotic, which means there's heaps of stuff inside.
So if they didn't have the wall, they'll essentially, because they're osmotic,
Yes,
water would just rush in and explode them.
that's right. So water rushes in, explodes them, but they, I should say, have a cell wall which maintains the structural integrity and stops them from exploding.
All right.
But what's this cell wall made out of?
Peptidoglycan.
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 That's
so
right.
That's a protein and a sugar?
That's, sugars and proteins click together.
Okay.
And so when we have a look at the differences, we can, again, exploit the differences because there's antibiotics that just attack that cell wall.
And these are some of the most common or popular or well-known antibiotics that particularly target cell walls.
That's right.
Which, I mean, everyone would have heard, penicillin. So these antibiotics work at this point.
Yep. That cell membrane that we spoke about,
Yep.
there are antibiotics that can disrupt that by depolarizing them. It changes the charge of the membrane.
Yeah. Okay. So that will affect theirs, not ours.
Yeah, makes it leaky.
Okay.
And the last difference. Or do you want one more, or do you want to go through multiple more differences?
Are there more?
Well, I'm sure I can.
Pretty sure this is the last one.
Okay, last one is.
So this is number 6.
Put your mouth close to the microphone for me, Matt.
I'm always swallowing it.
You need to put. How about you put your nose on the filter for me? There we go. Stay there.
Now I can't see anything.
That is perfect. Okay, so metabolism.
Go on.
Well, there's some metabolic differences. You want to know what they are? Folate synthesis.
Or folic acid. B9.
Is that what it is?
I think it's B9.
Okay. Well, at least it's benign and not.
Well, okay. So that's a poor joke.
Yep.
So folic acid, why do we need it?
I don't know. Why do we need it?
It plays an important role to create nucleotides and amino acids.
Okay.
So if you run out of your folic acid or folate, you're going to have all sorts of problems with, again, the DNA, RNA, protein synthesis.
All right. So do we need folate, humans?
Yes, we do.
Okay. And bacteria need folate?
Correct.
So if we give them an antibiotic that affects folate, won't it hurt us?
You would think that, but we have a gastrointestinal tract, unlike they do.
Okay.
So that means we get it through our diet.
So bacteria don't ingest folate, they create it themselves.
Correct. Yes.
Okay, so that means we can inhibit the enzymes that make the folate.
That's right. Yep.
All right. Okay, is there anything else metabolism-wise? There's one. It's not one. There's actually multiple other metabolic processes that antibiotics can attack and disrupt.
Okay.
There's too many to mention though. Because they're so variable.
I'm glad you brought it up.
Well, I'm just going to say only because there's a type of antibiotics which we might bring up which can affect multiple metabolic pathways.
For example? Or you just don't want to even mention it?
I don't want to mention because it's things like electron transport chain stuff. It's
or like NADH.
well, how's this? Here's something interesting. So when we make energy, ATP, how do we do it?
Put glucose and oxygen together and we get ATP.
Okay, where? Where does this happen?
Usually the mitochondria, but you can make it in your cytoplasm.
Okay, so do bacteria have mitochondria?
No, but they make it across their membrane because it's thought that our mitochondria came from a bacteria.
Because that's right, bacteria are mitochondria. So they don't have mitochondria themselves. They've got all the proteins for the electron transport chain.
Oh, good point.
Like you said, embedded in their walls. So
Not walls, membranes.
Oh, membranes. I made the classical faux pas.
So does that mean that because a mitochondria has 2 membranes,
Yeah.
does that mean that it has to have come from a gram-negative bacteria?
Well, I don't know how old gram-negative, gram-positive bacteria are. Maybe they're not that old
Okay.
because there's no mitochondria that lives by itself as far as I'm aware.
All right. So if our mitochondria are old bacteria that we've just utilized and they've just stayed with us, does that mean it has DNA in it?
Correct.
Okay. Is it like a plasmid?
Correct.
Oh, that's awesome.
Yeah, so mitochondria is circular DNA.
And is that where you get the DNA from your mother through that method, mitochondrial DNA?
Yeah. So if I were to take the mitochondria from your body and compare them to your mother's mitochondria,
It's the same.
mitochondrial DNA, and your father's, they would match your mother's, not your father's.
Oh, right.
Why?
So it's because my mother's
A winner.
my mother's ovum
Oh, okay, let's not talk about this.
egg contained the cytoplasm to make me. The first cell that was me, Matthew, was a 1-cell zygote, which essentially was my mother's complete cytoplasm and her DNA and just my father's sperm DNA. That's it. Nothing else.
But that doesn't explain for us. Well, what about the mitochondria in your father's sperm?
He just offloaded his DNA into the
Oh, that's
cell.
a terrible word to use. All right. That's a terrible term.
It just, I'm not going to say that.
It's a dilution factor thing.
Really? I'm pretty sure I could be
The
wrong
ovum
here.
is the largest sorry, the ovum is the largest,
Cell.
one of the largest cells in the body. And
Right.
the sperm is one of the smaller cells in the body.
Yep.
And so when the sperm buries its head inside of the egg where the mitochondria is, it's just
Does it
gonna
actually
dilute.
go in, or does it just the DNA gets released into the cytoplasm?
No, you get father's DNA inside as well.
Oh, do you?
Yeah,
Okay, so it's just a dilution.
diluted out.
Okay.
Look, I could be wrong. It's biology. I probably am wrong to some degree, but I think that's a nice simplistic way of looking at it.
Okay, I didn't know we would get to this.
Neither did I. Okay, at least we've spoken.
How I was created in an antibiotic podcast.
Yes. Well, I think, well, you're the embryologist. No wonder you always bring this up. So we've spoken about the differences between us and them, and we're going to do this tribal thing, us versus them. Now,
I think we should just do a quick wrap up because I think we got caught up in a lot of detail. So the differences are, let's start from the outside of the bacteria and work our way in. We've got a cell wall on a bacteria where our cells we don't.
correct.
That's one way. Their cell membranes are slightly different.
Okay, so can I do a wrong one? Let's do this one.
Is that crickets?
That's crickets, maybe.
Maybe that one.
No. I want one that's like a tick.
That's applause, isn't it?
Yeah, that's applause. Okay, maybe we shouldn't figure this one out live on air.
I think we should probably
This one.
predetermine it.
Okay, so every time you say something, this will come up.
Is it just a
There's a bunch
ding
of
or
people laughing.
Okay, so we've got bacteria have cell walls. That's one method. The membranes are slightly different. That's another method. Their way that they unravel their DNA, that's another method. They've got different ribosomes. That's another method. And then finally, the way that they make the folic acid, that's another difference. So there's 6 ways we can essentially try to kill bacteria off
Yep.
without hurting our own cells. Is that right?
Yeah.
Okay. And this is the 6 categories
Yeah, well, 5 or 6. 5 to 6.
of antibiotics. And
Of
under these,
mechanisms of actions of
yeah,
antibiotics.
and under these, there are multiple classes with many, many, many kind of brand or generic names,
Yeah, there's so many.
which we're not going to go through.
No, because you'll turn off.
Yep.
I'll turn off.
Okay.
All right. So next step now, Matthew, is what's the difference between? Well, we spoke about the difference between gram positive and gram negative.
Yeah,
You
so
want to talk a little bit more about it?
basically, this is to do with the outside of the bacteria. A gram-negative bacteria has a membrane on the furthest outer region, and then if you go slightly inwards, it's got now a cell wall, and then it's got another membrane.
And it's a pretty pathetic cell wall too.
It's much thinner than a positive gram-positive bacteria.
Yeah.
And what is it made out of?
What's what made out of?
The cell wall.
Peptidoglycans.
Okay. The only other difference that I can think of there's probably millions. We're not microbiologists, but one of the main differences with gram-negative, there's also a liposaccharide.
Lipopolysaccharides, LPS.
That helps to reinforce the membrane to the wall.
That's right,
correct?
on the outer layer.
Okay. And this is important more clinically because if you annoy these bacteria, like
Matt annoys me.
Gram-negative bacteria, annoy them, or if you kill them,
Yeah.
they release these lipopolysaccharides. Is that right?
Correct.
And it becomes an endotoxin.
Ooh.
Is that right?
Yeah, that means a toxin from within.
And this is potentially very dangerous because these toxins can kill us or kill our cells.
Yeah, it can result in shock.
So this could be actually a method of septic shock.
Yeah,
Yeah.
that's right. So what is that?
Well, it's basically where you have this huge amount of release of these toxins and your body reacts to it in a way that is so severe, your body goes into a form of shutdown. So your organs will start to shut down, and the way that your cardiovascular system may respond is vasodilate.
So it's like a systemic inflammation.
Yes.
Everything dilates and fluid drains out.
And if you dilate all your blood vessels, then your blood pressure will drop through the roof. Well, it's not through the roof, through the ground.
To the floor.
Yeah.
Yeah.
So
it goes from the roof to the floor.
You go hypotensive.
Yeah.
And you probably go into multi-organ shutdown and so forth.
Because things aren't getting fed.
With oxygen.
Yeah. All right. So,
okay, compare that to the gram-positive bacteria.
Yeah.
These bacteria have super, super thick walls at the outside reaches.
Yeah.
And then on the slightly inside that is just one membrane.
Wow.
But the important point here is the
peptidoglycans.
Yeah, is very thick.
Yeah, very thick.
In comparison to the negative. So the reason why it's called gram-positive versus gram-negative, there is a certain staining technique that is done where if you stain it with, do you remember the names? There's like violets. And
gram staining.
Yeah, but there's a violet stain and there's a wash and so forth. So basically, when you put the first stain, I could be completely wrong here, but this is the crux of it. When you put the stain in with one of the, I think it's a gram-positive, you get stuck behind the wall of one and not the other. And so when you put your wash on, for one of the grams, it washes away and the other one, it stays stained.
That's right.
And then you know the difference between a gram-positive and a gram-negative bacteria.
Yeah. I did it 20 years ago.
Haven't you done a video on this?
Yeah, probably. I've done a video on everything. Doesn't mean I remember it all.
Okay. Any other differences with bacteria that's important to know?
No.
That was simple.
Yeah, that was easy.
All right. So with these antibiotics, with these mechanisms, we're going to target the bacteria. An important thing just to be aware of is sometimes when you utilize these to kill them, it can be a difference being bacteria. So these antibiotics can be what we call bactericidal versus bacteriostatic.
What's that mean? What's the difference?
So cidal means death. Okay. Static means stoppage. So for instance, if you block the way that protein synthesis is made within the bacteria cell, so what's this? This is the ribosomes. If you block them, then essentially the bacteria lose its ability to make new proteins, so it will kind of slowly die off. Or if you stop its folic acid production.
Okay, so bacteria static just stops it and ultimately it'll die because it's not undergoing its normal metabolic
processes. It can't reproduce, so its growth curve diminishes and it slowly plateaus off.
And the bactericidal it kills it.
Yeah, so
this
is more to do with the cell wall one. So if you just break the walls, then all the water rushes into the cell and it explodes and it's now cidal.
Okay.
So bactericidal.
All right. So when we go through these different classes of antibiotics, do you want to go through by looking at their mechanism of action, then talking about some classes that sit within each? Is that how you want to do it?
I think we should do it mechanism by mechanism.
All right. So which mechanism would you like to begin with?
I think we should start with the cell wall inhibitors.
Okay. So the cell wall, like we said, made up of peptidoglycans. Now let's go. Can we go into a little bit more detail about this cell wall?
Yes, you can go nuts.
Oh, thank you. So peptidoglycans made up of sugars and proteins, hence it being called peptidoglycans. When we look at the sugars or the glycans, there's two major types. There's N-acetyl muramic acid and there's N-acetyl glucosamine. So NAM.
Is that like what you take for your joints?
Yeah, it's basic. But the thing that you take for your joints doesn't actually help your joints, just to let everybody know.
Ah, okay.
Waste of money. So NAM and NAG, N-acetyl muramic acid, N-acetyl glucosamine, and they click together. So they are two sugars that click together. Now, attached to the NAM, the muramic acid, is about 5 amino acids. All right?
Right.
And now we've got a subunit that can, basically the building blocks that can build the wall, the cell wall. And what we need to do is click the walls together. And there's two different ways you can click the walls together. You can continue to click the sugars side by side to lengthen the wall.
Yep.
Or you can click the proteins together, or the amino acids together, I should say, to make a new layer of the wall. Does that make sense?
Oh, yes. Okay.
Okay, so if you want to elongate, you click more sugars side by side. So it goes NAM, NAG, NAM, NAG, NAM, NAG, NAM, NAG, NAM, NAG.
Sounds like a relationship.
Tell me about it. And then attached to the NAM, sticking outwards perpendicular, is going to be the amino acids, and that binds to the next amino acid to make a whole new row.
Outwards, so more
Outwards.
Superficially.
Correct.
Okay.
Right.
So if this was a wall that we're creating, what analogy can we use here?
I'm trying to think of a Donald Trump-based analogy, but I can't think of, because that wall won't be built. I think, what we've said is good enough, isn't it?
Big, huge concrete slabs, and you join them together with, say, mortar.
Mm-hmm. So the amino acids are the mortar, and the slabs are the NAMs and NAGs.
Okay.
Is that right?
Yeah, I think so.
Look, all analogies fall
later.
apart at some point. All right, we got that there. So let's now look at some antibiotics that break down the cell wall or stop its synthesis.
It stops the clicking together, these ones.
So either stops the NAMs and NAGs from clicking together or stops the amino acids clicking together.
Okay, and what are these known as?
Well, the ones that stop the amino acids clicking together, often termed the beta-lactams.
Okay, all right. And so this is, why is it called a beta-lactam?
Because of the molecule that comprises these antibiotics. It's called a beta-lactam ring.
Okay, so all these antibiotics have the same kind of structure to it, which is a beta-lactam ring. And what they do in the context of this stopping the cell wall of the bacteria, making new cell walls, is clipping the bits of the wall with the amino acid?
Yep.
All right. And so what are the ones that fit here? What are the antibiotics?
So there's three main types of beta-lactams that everyone should know. So there's the penicillins, old school, cephalosporins, which actually have 5 generations of cephalosporins, and the carbapenems.
Okay.
They're the 3 main that everyone should know.
All right. So do you want to start with one, or we just
We'll start with the
keep them as
penicillins.
group?
What do you reckon? Penicillins?
Yeah.
They're the old school one. What do you know about the history of penicillins?
Well, usually people associate the knowledge of penicillin with Alexander Fleming.
Yep, the guy who wrote all the James Bond books.
I think it's a different guy.
Oh, okay. That's Ian Fleming. Sorry.
Okay, well, let's take a step back. Basically, we knew penicillins come from mold, which are funguses or fungi. Okay?
Some people say I'm a fungi.
Yep. So the so the Egyptians.
I pressed the wrong one.
Okay, so the Egyptians, the Chinese, the Greeks, the Romans, even your relatives, the Serbians.
Oh, okay. Here we go.
They knew that by applying moldy bread
Your relatives, moldy bread.
to wounds, so topically,
Yeah.
there would be some benefit in reducing the infection.
So they took moldy bread and rubbed it on their open wounds.
Well, potentially. I didn't really go into the depths of how they did it, but it was just known that moldy bread had some effect on infections.
How do you reckon they first did that? How do you first discover that moldy bread helps your wound?
No idea.
Yeah. Okay.
All right. So then we go to, well, it's thought that Alexander Fleming was the man. And so in 1928, he actually isolated and first discovered penicillin.
Yeah.
However, historically, there was something known with mold for this case. Now, going back to 1870, there was a guy called John Burton Sanderson. So he found that...
Is he the guy that started KFC?
Not that I'm aware of.
Right.
So this guy found that if you got a petri dish and you had mold growing in it, if you got the juice of the mold and squirted it onto... Squirted that juice onto a petri dish of bacteria,
yeah,
that would stop growing. Okay?
How's he figure that out?
I don't know. Again, you're thinking that I know the details here. Okay? I don't.
Sorry.
I just got a few names and a few facts.
Just thought you did your research. That's all.
So then we move on to a guy called Joseph Lister. Now, I read a book about him.
Because I purchased it for you for your birthday.
Very nice. Very nice of you. So he was a surgeon, I think, in Scotland, and he was one of the first guys that started to be able to piece together infections from certain things by poor hygiene practices.
So is he the one that started everyone washing their hands?
I think he was a big player in that.
Oh.
And so he found, moving on from John Burton Sanderson, he moved and he found that the same kind of juice could be useful to decrease bacterial growth in human tissue.
Right.
Okay. And so he probably created some compounds from that. And one of them, so his name's Lister, and this is where Listerine comes from.
Oh, okay. Really?
Yeah. Possibly not. Well, it's probably an alcohol wash that was used for other things, but obviously now we use it for mouthwashes. But whether they used it in wounds, I'm not sure.
Listerine, what does the current Listerine have in it now? It's not ethanol, is it?
No, they got rid of it because there was an effect that when you metabolized it in your mouth, it became carcinogenic.
Right. So it did the opposite of what we wanted.
Yeah. So then we moved on to 1897, and there's a guy called Ernest Duchesne. Okay, so what he found, I presume he was English. Now, he observed in the Ottoman Empire that Arab stable boys used a moldy mixture to topically place on saddle sores, which with a beneficial effect.
Wow.
Of reducing the infection. So then he basically took that idea, because he presented this in Oxford to the, what is it called? The
Royal
Academy?
The Royal Society.
Yeah, that's right, yep. And he found that he used this mixture to treat typhoid successfully in guinea pigs.
Well.
I'm not sure how you give guinea pigs typhoid. Just the runs.
You'd have to
feed them fecally orally.
Yeah.
All right. So those three examples, I'm just illustrating that it wasn't actually Fleming necessarily that came up with it. Okay. So now we jump to 1928. Fleming essentially isolated and now understood it was penicillin per se. Now, he didn't do a great deal with the penicillin. He either ran out of money or he ran out of time or interest.
I heard that.
And he let it go.
Well, I heard that he, for the better of mankind, didn't want to patent it so that everyone had the opportunity to have access to it, so it wasn't ridiculously expensive. So there was no patent, so it was open for every medical company to be able to produce.
Could be right. He definitely stated that it was difficult to go from what potentially, or the translation from what could be in the lab versus what can be clinically used medicinally.
Oh, really?
So he maybe just thought it was too difficult and let it slide.
Because I think back then it was something like it took tons and tons of like vats filled with tons.
Yeah, this comes to this point.
Yep.
So then it wasn't until about 1940s where we had Florey and Chain. So again, Oxford.
Are they two people?
Two people.
Florey and Chain.
Yeah, Chain, last name Chain. I'm not sure. Howard Florey, not sure. Maybe Joseph Chain. I could be wrong here.
Billy Bob Chain.
So they came up with the purification technique. And so they...
what are they making it from? Mold.
Yeah, mold.
So they have vats of mold.
Yeah. So this is where it gets interesting. And this goes back to, I didn't find this in my research, but I remember it some time ago. They isolated it and they started to use it clinically. Now, the first well-known use was a policeman that had a serious infection. I think he had septicemia or it was close to it, and they started to apply the penicillin mixture.
Intravenously?
Not sure. It's a good question. Was that the right button?
No, I did the laugh.
Okay, so because they were the amount they had was very finite, they had to recycle it. So they were actually getting his urine and extracting it from his urine and giving it back to him.
Wow.
So it had a good effect, but they ran out of it.
Yeah, I assume each time it would be diluted.
And so he
died?
Improved and then he dropped off and died.
Oh, no.
So remember, this is coming into kind of World War II period. And so resources were low and the government probably couldn't give a whole lot of money to develop this particular antibiotic. And so what they were doing to grow, this is my understanding, what they were doing to grow the penicillin was they were just trying to have in the hospital certain containers that you could have a whole lot of water with a great deal of surface area and little volume. So they were putting water in bedpans and all sorts of things to grow the penicillin in. But they couldn't do it well enough. So I think then they moved across, or they took the idea, because as I said, Britain was in the war. They went across to America and they ran the idea to a couple of companies. One particular company, which was more in terms of hydraulics, I think, was a company called Pfizer.
Yeah.
It wasn't a drug company.
I know the name.
And what it could do is it could get big vats of water, because the limiting factor is the mold needs oxygen to grow significantly.
Yeah.
Otherwise, it would just die off if it's actually in the water. It has to be exposed to the air. So I think what Pfizer could do is they just aerated the water, because it was a company that dealt with hydraulics. Or is that the right word?
Hydroelectric?
No, it's not electric.
Hydraulics is pressure.
Anyway.
Water pressure.
So basically they devised a technique which basically you could put the mold into the water but pump air through it, and the fungus grew well and they could extract a whole lot more penicillin that way. And then obviously Pfizer became super rich and became a pharmaceutical company.
Okay. All from penicillin.
Well, I don't know. But that's...
Okay, so penicillin, which is the first antibiotic.
It's going to be a long podcast.
No, it won't.
This is the main one. This is the main one.
Yeah, this is the main one with the probably longest history. So penicillin can inhibit cell walls, and it does it because it contains a beta-lactam ring.
Mm-hmm.
And what the beta-lactam ring does is it stops a particular enzyme called transpeptidase. And what transpeptidase does is it clicks together the amino acids from one NAM to another NAM. So basically, anytime bacteria want to make another layer to their cell wall, they need to click the amino acids together. Transpeptidase does this, but luckily, our beta-lactam ring slots very nicely inside of the transpeptidase and stops the transpeptidase from being able to click these bits of cell wall together. And that's how penicillin works. In actual fact, that's how not just penicillin, but other beta-lactams work, which include the cephalosporins and the carbapenems. You okay with that?
Yes. Are we going to talk about resistance here? Or
yeah, I think so. I think this is probably a good spot, because bacterial resistance. So this is where bacteria becomes resistant to the antibiotics. It's not us becoming resistant, it's the bacteria.
Yep.
And so penicillin was one of the early antibiotics being used, and therefore one of the first two bacteria to become resistant to.
I think it's also important just to put in here that because penicillin came from fungi, which is a microbe in the environment, a lot of antibiotics are actually naturally occurring that are produced from other bacteria or microorganisms. And so microorganisms have been battling out in wars amongst themselves for billions of years. So they've been using all these chemical warfares among themselves for a long time. So bacteria probably have already dealt with penicillin before, and so it had an arsenal to fight against it. Okay.
That's a good point. And I think another point, just to make a really nice comparison, is that mutations happen in all organisms, and mutations are genetic changes which can affect the way genes are read into proteins. And so sometimes the mutation has no effect and they make the same protein. Sometimes it has a detrimental effect and the protein doesn't work. Sometimes it has a beneficial effect and it amplifies or changes the activity of the protein. Now, the thing is, when we get these mutations, we don't really notice them until our next generation, which is often, 20 or so more years, right? But for bacteria, sorry, I just dropped my notes. For bacteria, depending on the type of bacteria, if we take a bacteria that penicillin kills off, or at least that category of the beta-lactams kills off, like Pseudomonas, they double every hour. Now, that means that if a mutation sporadically or randomly happens into that Pseudomonas, every hour, one Pseudomonas with the mutation will turn into 2. And then in the next hour, 2 to 4, and the next hour, 4 to 8. And then what you'll find very quickly, very, very quickly, there's going to be over 1 million to billion Pseudomonas bacteria within a few days. All right? So it does not take very long for a mutation within a single bacterium to spread throughout the entire colony. Now, this is the thing. The mutation is random. So it can just happen in any single gene. But because what we have is, 1, there's heaps of bacteria. 2, their doubling time is so quick that it's not unlikely, even though statistically for a single bacteria, it's unlikely for a mutation to be in a particular gene. It's not unlikely that it will occur because there's so many opportunities for this to happen. And if the mutation happens inside of the gene that transcribes the transpeptidase that clicks the walls together and changes its shape, so it has the same activity, but the beta-lactam ring from the penicillin cannot bind inside, it's now got resistance to the beta-lactam ring. So that's only one of the 2 ways in which this can happen.
So this was the resistance? So
that's one type of resistance. There's another type. This is just the transpeptidase, specifically the penicillin binding protein, which is a subcategory of transpeptidase. This is one way it can gain resistance. But there's another way, and this is because the only way that you and I, maybe not you and I, the only way that human beings can share DNA is when male, female create offspring. That's the only way they share DNA is by creating another offspring. But bacteria, one bacteria can come to another bacteria and actually, while they're living, share DNA. And so you can have a bacteria that has a particular gene that one bacteria doesn't, and give it that gene, and that gene, for example, may translate into a protein that now has that is an enzyme.
So this goes into its plasmid.
That's correct, which is an enzyme that can now break up beta-lactam, and that's called beta-lactamase.
And can these genes be just floating around without a viable bacteria?
Yeah, so if you've got a dead bacteria, a live bacteria can suck up the DNA.
Right.
Yep.
So is there a term for this?
There is, and I've forgotten it.
Is it called something like lateral?
It's something like lateral gene transfer.
Lateral genes transfer,
yeah. Lateral is from one to another. Horizontal is offspring.
Oh, maybe it's horizontal gene transfer.
Oh, sorry, yeah, it's horizontal. Yeah, because it's going from one to another. Yeah. Lateral is from
live ones.
I don't know now.
Anyway, it doesn't really matter.
Anyway,
okay. So the crux of
but those two are different methods of resistance.
The crux of the point here is these antibiotics, which are penicillins, monobactams, cephalosporins, and carbapenems.
Yeah, I didn't actually bring up the monobactams.
They are beta-lactam enzymes. Sorry, beta-lactam
class of antibiotics.
Yeah. And you're saying a resistance that occurs is bacteria start to produce an enzyme to break the beta-lactam ring. And this is called a beta-lactamase.
That is correct.
And so we saw this pretty early on in the creation or the production of penicillin as an antibiotic. So it was shortly after when they were first used, we started to see resistance starting to occur. And Fleming actually predicted this. He actually said there'll be such a need for antibiotics that it will cause a problem with resistance. And that was in the 1940s.
Well, we're saying it. I mean, the projection is that by 2050, more than 10 million people will be killed due to antibiotic resistance, which is a lot of individuals. I mean, there's bacteria out there now that cause infections for us that we're pretty close to not being able to kill off. And one of which is the STI gonorrhea, right? Gonorrhea is really
What did you look at me for?
Well, I just thought that's one that you would know. You've got a lot of koala friends, don't you?
Well, let's move on.
That's the STI that koalas get, isn't it? Gonorrhea? I think it is. And methicillin.
No, it's chlamydia.
Oh, it's chlamydia. They're both STIs. Chlamydia is also another one, but methicillin-resistant Staphylococcus aureus.
Well, I was going to get to that. So basically, we
staph.
then created methicillin as a counter to.
Is that a cephalosporin?
It's a counter to the.
Is that part of penicillin or is it cephalosporin?
I'm not sure exactly, but it was used for penicillinase resistance.
Yep. Oh, okay. So penicillinase is, again, the same mechanism by which you've got the mutation that occurs to allow, or the gene transfer that occurs to allow for an enzyme that breaks down beta-lactam. There's another enzyme that bacteria can evolve or mutate and have that actually breaks down other aspects of penicillin. So penicillin isn't just the beta-lactam ring, it's other things.
Yeah.
But if it breaks down the penicillin as well, it's also going to inactivate the penicillin's ability to kill off the bacteria.
Okay. So
does that make sense?
Yeah. So methicillin was brought in 1959 to counter bacteria that was resistant against penicillin because they produced the penicillinase enzyme.
Yeah.
And so it was brought in then. But interestingly, shortly after that, then you had like particularly Staphylococcus
aureus,
which is golden staph.
That's right.
Became resistant to methicillin, and this is where we get the term, or it's not an abbreviation. What is it called?
MRSA.
Yeah.
Methicillin-resistant Staphylococcus aureus.
Yeah, I'm just saying it's not an acronym. It's
an abbreviation.
No.
Yes.
Oh, is it?
Oh, an initialism. Sorry.
Initialism. Yeah.
Yeah.
So one final point is then we brought in some antibiotics to counter the bacteria that was producing the beta-lactamase. So these are beta-lactamase inhibitors, which are antibiotics. And so the first one that we found actually came from a bacteria itself called Streptomyces calavolgens or calavolgens. And this is where we got an addition called clavulanic acid.
So we're using it against itself.
Yeah. So certain antibiotics use clavulanic acid with amoxicillin, which is a derivative of penicillin.
So it's common to use antibiotics together.
Right. And this kind of gave us or led us into the carbapentins.
No, carbapenems. There's no pentams.
Yes.
You're thinking of gabapentin, which is a
carbapentins.
antipsychotic.
And so in the final point I'll put here is the penicillin and the cephalosporins, I believe, are most resistant to the bacteria that produce beta-lactamase, whereas the monobacteriums and the carbapentins, their beta ring is not quite the same as the penicillin and the cephalosporins, so they don't have such an issue with the bacteria producing the beta-lactamase.
Okay. All right, so we've done the beta-lactams. What about, are there any other antibiotics that kill off, or I should say, stops the synthesis of the cell wall? Maybe
yes,
something like
glycopeptide. I'll just put one final addition and then we can move on. And this is just the side effects. The common side effects of using drugs that with a beta-lactam ring is going to be nausea, vomiting, diarrhea. They're very common. Most antibiotics will have this problem, nausea, vomiting, diarrhea. But an important one just to be mindful of for beta-lactam antibiotics is allergies. And this can range from a reasonably benign rash all the way through to anaphylaxis. Okay.
So do we know why? Is it just because our body's recognizing the beta-lactam or something about that drug as foreign? Is that all it is?
It's particularly penicillins. I'm not sure if it's all the beta.
Penicillin's the most, but no, that you can definitely have it with the cephalosporins.
Okay.
With each generation, you can have rash and allergies and so forth.
Yeah, I'm not sure.
Okay.
moving on. So we're still in the cell wall, but these aren't cell wall synthesis inhibitors through beta-lactam. These are through peptidoglycan, peptidoglycan.
You were right the first time, peptidoglycan.
Okay.
Or did you just say peptidoglycan? Peptidoglycan.
So a big one in here, or the classification here is the glycopeptides, right?
Yeah.
And also the polypeptides.
Yeah, glycopeptides, polypeptides, they're two that can affect the synthesis of the cell wall as well.
So one of the big difference with these cell wall synthesis inhibitors, these class of antibiotics, is it's not like the beta-lactam ones where you had a finished wall and you're just clipping it together. Okay.
Yeah.
These ones more have an effect on creating the wall to begin with. So the building blocks of the actual wall. So the actual creation of the individual little blocks, let's say, are these categories. So these are things like phosphomycin, vancomycin, cycloserine.
Yeah, like vancomycin is a glycoprotein, for example. A glycopeptide, I should say.
Yeah, so this is more to do with getting the little building blocks together to put big chunks of the wall together.
Yeah, so we said earlier that one way of, beta-lactam stops the amino acids from clicking together. We're just stopping other parts, the glycans, from clicking together.
Yep, okay.
And other aspects of the amino acids too. So it's just having different cell wall clicking together effects.
Right.
Yeah.
Just an interesting point in history for the production here is around the 1950s it was essentially considered the golden age of antibiotic production, creation. Streptomycin was one of the first antibiotics that we derived from soil. So in the 1940s, we isolated it from soil, probably from other bacterial microbes within the soil. And there was a company called Eli Lilly, a lab that was quite involved in creating new antibiotics. They found that deriving the antibiotics from soil was something to look into. So they actually broadcast to a whole lot of Christian missionaries to send soil back from their exotic regions of the world.
Okay.
And a sample came...
Just to see if they could find something new.
That's right. And a sample came from Borneo.
Okay.
And they...
Where's that?
Malaysia,
all right.
I think.
You're right.
They isolated vancomycin from this soil from Borneo.
And that's a glycopeptide.
Yes. And vancomycin comes from the word vanquish.
Ooh, like get rid of.
And this was particularly important because we had a whole lot of penicillin. So when vancomycin came in, I haven't got the date when it was first isolated or used. It came about because we had a whole lot of penicillin-resistant staph at this point.
So vancomycin was a lifesaver.
That's right. However, early in its use, it was referred to being called Mississippi mud. Not sure if that was how it looked, but it caused a lot of problems. It became quite seriously nephrotoxic and ototoxic, which means damage into your kidney and damage into your inner ear.
Why ear? I get the kidney.
Don't know.
Okay.
It's in the cochlea, or is it the cochlear nerve?
Is it the nerve it affects?
I'm not sure. Yeah, I'm not sure. That's a good question. A lot of these drugs they become...
There's some pretty weird things, don't they?
They do. They call neuropathies, a lot of neuropathies. So
nerve damage.
Whether that was specific to the cochlear nerve, I'm not sure. But vancomycin has always been pushed to the side and been a last resort antibiotic, possibly because of its side effects profile.
Is it broad spectrum?
I don't think so. I think it's relatively narrow. But please check that. What was I going to say? I lost my train of thought.
I apologize. I don't know. You were saying that.
Just because
the last resort.
It was first used because of all the issues with penicillin resistance. But as we said with the last point, when we started to use the other additional, the chloronic acid with the penicillins and so forth, that overcome some of the issues that we were having with resistance to penicillin. So it has been used as a kind of a last resort in clinically anyway.
So if there's something like Staph aureus, right, which we know is methicillin resistant, vancomycin would be one of those go-to antibiotics.
I believe so, yes.
Yeah. Okay. All right. So what about just quickly, I don't want to spend too much time on this one, but the cell membrane disruption. So we've spoken about, are we okay to move away from cell wall synthesis?
Yeah, we're all done.
Okay. So everyone applauds because, wait a sec. No, that's well, you're welcome. Cell membrane disruption. So lipopeptides are one example, which basically can disrupt the depolarization of the cell wall. And this depolarization of the cell wall means that the cell can't really do much.
Yeah.
And therefore it's gone.
There's two types here, daptomycin and polymyxin. So daptomycin is more successfully used for gram-positive bacteria. What it does is somehow it incorporates calcium into the cell membrane of the bacteria, causing it, similar to what happens to Michael, it becomes leaky.
Oh, no.
Particularly leaky to potassium. So this is what you spoke about earlier for what, action potentials or something? Is that no? They wouldn't have action potentials.
So depolarization. They don't have action potentials, but they do have a charged membrane.
Okay. So potassium channels become leaky. Presumably, the potassium leaks out of the cell, which would affect something in the cell.
Yeah. Look, it's just unbalancing out really important homeostatic ionic balances.
Yep. And the other one is polymyxins, which are better utilized for gram-negative bacteria. They just change, again, the permeability of the outer membrane of the gram-negative bacteria, which then can permeate into the inner membrane, and then it becomes, I don't know.
Done in.
Yeah.
All right. What are we moving on to now? What type of mechanism of action? We've done cell wall synthesis inhibition. Well,
I think let's do metabolism disruptors, which is folic acid.
Okay. Yeah, I'm not going to bring up the other one. The other one is nitrofurantoins. And the nitrofurantoins have multiple effects. They're usually used for UTIs. And they block and inhibit so many different metabolic pathways. I don't even want to bring them up. So let's talk about the sulfonamides.
Sulfonamides. So these are drugs to block folate on folate synthesis. And surprisingly, Michael, this was the first drug, this category, the first antibiotic used historically.
Well, I don't believe you.
Because everyone thinks it was penicillin. In fact, it's sulfonamides.
Sulfonamides.
So I'll give you the history and then you can talk about how it works.
Yeah.
So late 1800s, now we go to Germany instead of England for the penicillin.
Finally.
Germany, Bayer, the company Bayer.
Hey,
we spoke about Bayer when we did
opioids.
Penicillin. No, sorry, not penicillin. Paracetamol.
And opioids.
Yeah.
Did we do one on barbiturates?
No.
Okay.
So
must have just been me.
Bayer was exploring the use of dyes, okay, particularly on staining bacteria, okay, but also on killing bacteria.
Yeah.
And there was a guy called Paul Ehrlich, okay, Paul Ehrlich. So in the 1850s, he found that he was using certain dyes for histology purposes, but he also found that some were toxic to bacteria.
Mm.
And he created an agent called salvaricin, which was arsenic-based and was used in 1909 for syphilis with some effect.
And did it work?
Yeah, it had some effect for syphilis, but
so you're fine now?
The fact that you had arsenic in it probably wouldn't do well with side effects. Yeah. So Bayer moved on from this, and it found that use in sulfonamides. No, this is a different derivative.
Oh, okay.
Plus a dye, they created a product called Prontosil.
So I don't get the dye. If it's just a colouring.
Yeah, I think it's the chemical properties of it.
Okay.
So Prontosil. This was first used in 1931. So this was 14 years before penicillin, let's say.
Wow.
It was shown to be useful in streptococcal infections in mice.
Yeah.
Okay. And then in 1933, its first use was for a boy that was dying of a staph septicemia infection.
Oof.
And it was successful in this case, unlike the policeman with penicillin.
Yeah.
Okay. And they discovered that Pontosil, so the dye portion of it, wasn't that useful at all. It was actually it being metabolized into the sulfonamides. Sulfonamides, yeah. So this is the starting point for sulfonamides. And it's thought, I couldn't find it 100% being proven here, but it's thought that Winston Churchill got saved by this class of medication, and also FDR, Franklin Roosevelt's son.
Wow.
And in World War II, it was common to be in the first aid kit of American soldiers.
Not other soldiers?
As, well, not sure, as a powder. So if you had a wound, you'd sprinkle this particular antibiotic topically into your wound.
So I find it amazing that there was a world prior to antibiotics.
Yes, where you would have died from a simple infection or
Yeah. Would you have been dead by now?
pneumonia.
Of pneumonia?
Oh, pneumonia is a.
Have you had pneumonia?
A bacteria infection? No, I haven't had it.
No, I'm
But
just
you would
saying.
have died from it.
So do you think you would be dead now? Are there any infections, bacterial infections that you think you've had that you'd probably have carked it without?
Don't think so. I don't think I've really used a great deal of antibiotics, at least for
good.
infection purposes.
Okay.
You use them prophylactically. Like, I mean, when I told you I fell off a fishing wall into the oysters, I think I was given it then, but that was just to prevent it.
Now, do they still prophylactically give antibiotics knowing the issue with antibiotic resistance?
Yes. Surgically.
Yep.
Yeah. And that's one area that they really have to look upon that.
Whether it's
might
worth
need to-
doing.
Yeah, that might have to change.
Yeah. Okay. So
Well, surgery was a big one. So many people wouldn't have survived surgery
yeah.
before antibiotics.
Yeah, true. Yeah, very true.
Very
Especially
low-
if they didn't have aseptic technique.
Very low success rate. So things like open heart surgery, no chance.
Yeah, of course.
Yeah.
Oof. All right. So are we done with the metabolic disruptors? Oh, we didn't
Well,
really
you didn't
talk
really
about
explain it.
how it works. So, well, simply put, like we said earlier on,
So these are sulfonamides, by the
these
way.
are very good. That
Was that right?
was good, yeah. You don't even have a headphone on, you don't know. So when we look at sulfonamides, they inhibit folate synthesis. So bacteria have the enzymes that can make folate, or the enzyme that makes folate. And this is a synthetase. Now, we don't have it, so it doesn't affect us. So you inhibit it, easily done, no folate synthesis, which means no synthesis of nucleic acids, which means anytime a bacteria wants to make new DNA, synthesize new DNA, it can't do it. Anytime it divides and requires more copies, it can't do it without folate.
Right. And as we said, that's to do with making nucleic acid and amino acids. So it just runs out of these building blocks.
That's what I said.
Okay, great. Okay. So what are the main ones in this group? Sulfonamides and trimethoprim.
What is it?
How come you haven't got trimethoprim up
I
on
don't
the board?
even know what that one is. Pass it here. I want to have a look at how you're reading that one. Where is it, down the bottom?
It's definitely trimethoprim.
Trimethoprim. Yeah, okay. Trimethoprim. So it's not a sulfonamide, but it's a metabolic disruptor.
Yeah, it's for folic acid.
Oh, okay.
It just affects a different enzyme than the sulfonamides do.
Oh, okay. All right. Is that all for the metabolic inhibitors and disruptors?
Yeah, the main side effects just be aware of is, again, nausea, vomiting, diarrhea, but also there is some degree of photosensitivity.
Yeah, and I think because they're used quite often with UTIs, there can be some kidney issues and I think maybe some stone issues.
Oh, formation of stone.
Yeah. Did you say sensitivity to sunlight?
Yeah. So
Do we know why? Or is that just another neuropathy?
Don't think so. I think you actually get like sunburn. Because I remember one of my colleagues in ICU, she had a patient on, I'm not sure if it's sulfonamides or just some other antibiotics, but the patient where they had the fluorescent lights was getting sunburnt where the sheets weren't covering them.
Wow.
And the colleagues were like, what the hell is happening here? And she just said, check the antibiotic and the side effects. And that was an effect was
Jeez.
photosensitivity.
All right.
So we've done walls, membranes, and folic acid.
Yep.
So we're left now with essentially the DNA
stuff.
side of stuff.
Okay. You want me to start?
Yeah, I think you take over here because my history's done.
Everyone's going, thank Christ. It's been 1 hour. So let's talk about DNA synthesis. Okay, so we've got inhibition of DNA synthesis and we've got the enzymysins. Now, what the enzymysins do is they stop DNA turning into RNA. So that's transcription. So we've got transcriptional inhibitors. They're the enzymysins. Then we've got the quinolones and fluoroquinolones. And they're the ones we spoke about earlier on about the unwinding of the DNA and the replication. So this has to do with the gyrase and the topoisomerase enzymes, and that's what the quinolones and fluoroquinolones inhibit.
Mm-hmm.
Now, are there any other DNA synthesis inhibitors that you've got written down you want to talk about? Because they're the two main ones I wanted to talk about, and that's all I've really got to say about them.
So what examples did you have for the DNA strand breaks? Did you have any of those?
No DNA strand breaks.
Okay. But you had quinolones, which is for the gyrase and topoisomerase 4.
Yep.
And the rifamycin, which is blocking RNA polymerase.
But isn't rifamycin a quinolone?
Not that I've got here.
Or is it an enzymycin? Oh, it's an enzymycin.
Yeah, I've got it as specifically targeting RNA polymerase.
Yeah, so that's an enzymycin.
Okay.
All right. Any others?
No, they're the main ones.
All right, now the last one.
Do you want side effects?
Oh, yeah. Should talk about side effects.
Okay. So quinolones, this is basically all GIT related.
Let me guess. Nausea?
Nausea, vomiting, diarrhea. There is some degree of neutropenia,
Okay.
insomnia, and widening of QT intervals in ECG. So your heart.
And what about damage to the nervous system?
Neuropathies.
Yeah.
Yep.
All right.
And then rifamycin,
Yep.
side effects. This is an interesting one. Again, nausea, vomiting, diarrhea. But this was an interesting side effects I included was red to / orange fluid secretion. So your tears, saliva
Is this what yours look like?
may become orangey red color.
Why? Is this a metabolic byproduct of metabolizing this
I'd
antibiotic?
imagine so. So you cry in red tears.
Wow.
Okay.
Okay. Last one. Ribosomes. Yeah?
Yes, so we go into the protein synthesis inhibitors here.
That's right. Ribosome subunits 30S and or 50S. I'm not going to be specific. You might be about which one inhibits which, but here are mine. I remember them. I remember them by saying atom. So my ribosome subunit inhibitors: atom, A, aminoglycosides, T, tetracyclines.
How do you remember it?
Atom, ATOM.
Okay, all right.
Yeah. A, aminoglycosides. T, tetracyclines.
Yep.
O, I'm going to be just as bad as Matt here, oxalotinones.
Yeah, very
and
good.
M, macrolides.
All right, that's fair enough.
You good with that?
Yep.
And like I said, they either inhibit the 30S or 50S.
Well, I'll be
subunits.
specific. So the aminoglycosides are the 30S, specifically at the A site. Do you want to explain that?
Nope.
So where the tRNA comes in to bring new amino acids,
Yeah.
is that right?
Yep.
It's the docking point. It blocks that point. So that's the aminoglycosides. Now, this is important to know because
So it's a dock blocker.
yeah, all right. It is ototoxic, which is ear, and nephrotoxic.
Okay.
So they're important things to be aware of. And then the tetracyclines stop the additional adding on from the next tRNA. And these ones are also phototoxic. So those two, aminoglycosides, tetracyclines are the 30S.
Yep.
And then we go down to the 50S, which is the macrolides
Yep.
and the amphenocols.
What's that?
Which you haven't got here.
I don't.
And a good example of a macrolide is erythromycin. This particular
Urethra.
erythromycin, after the singer. This blocks the P site. So this is the exit site. This is where your elongating polypeptide chain exits. Is that right?
Sure.
In the ribosome.
You're acting like I should know this.
Yeah, you're the genetics man. This is your bread and butter.
Don't tell people that. This is beyond genetics. This is proteins. This is biochemistry.
Okay, so the macrolides, such as erythromycin, an example of side effects is nausea, vomiting, and you have ringing in your ears. So that's
Like tinnitus.
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 Are we done?
I hope so. That's a lot. I thought that this was going to be a short one.
Do you think we confused people more?
I think you did. I think I'm very good at getting good points across, and I think that you're confusing
With stupid history
at the best of times.
Okay.
I think everyone listens to you and they think,
Is that cricket?
and everyone listens to me and thinks, that's the guitar playing. I pressed the wrong one again. Anyway, sorry about that.
We need
everyone.
to change these shortcuts.
I think so. Or at least put some stickers on them to say what they are.
Maybe the listeners can send in some suggestions of what we can use for our shortcut
even
audio
better.
bites.
Even better, send us audio bites. If you send us a
that'd
good
be awesome.
audio bite,
Yeah, we will use it. Great idea.
100%.
Great idea.
So send us an audio. I don't care if it's you saying "Shut up, Matt." I'd like that one. I'd like one with the listener saying "Shut up, Matt." That'll be good. And then another one going, "Keep talking, Michael." Or another one that says, "Just before you finish."
Or can you just pause here?
Oh yeah, that'll be another. Can you just pause it? Or maybe one where it says, "Put your mouth closer to the microphone, Matt." We done?
Should we do any degree of wrap up?
No. I think everyone's had enough.
There are a lot of names.
If you want to wrap up, go back to the start where I spoke about what we were going to talk about.
Anything else in the resistance side?
No.
I think we've done it all.
Yeah, I think we're good.
So did you speak about why there is this resistance? So you said the mechanism.
Well, they don't want to die.
Okay, and
But
so
in actual fact, there's
you said
no,
there's
that's a lie.
So
That's a lie.
you said there's an example. One way it happens is de novo, right?
Yeah.
Which just means a spontaneous mutation,
Yeah.
which then can be passed on either to its children or not laterally, horizontally.
Yeah.
Correct.
Yeah.
And then there's also just genes in the environment that can just be sucked up and utilized. Mm-hmm. Is that right?
Correct. But remember, there's no intent here. So I said because they don't want to die. That's a lie. Bacteria have no idea what's going on.
How do you know?
Because, okay, so,
Look, you don't have.
all right, consciousness. Are we saying that now that
you don't have a
consciousness?
cell wall, so you wouldn't know.
How dare you? Consciousness, does it exist within bacteria? Does it exist within bacteria? What do you think? What do you think, listeners? Is there consciousness within unicellular life? Is there consciousness within Matt's life? Probably not.
Okay, so a final point in resistance is if you were to take an antibiotic, okay, regardless if it's been broad spectrum and narrow, have we used these terms before?
Well, I tried to bring it up and you ignored it.
Okay. Broad meaning it can target many species of bacteria. Narrow is it's focused in maybe a couple or one type.
Is it species or is it mechanisms of action?
I think it's species.
Okay.
And so if you were to take an antibiotic, it doesn't really matter if you took it orally or IV. As you said, there's 2-to-1 bacteria to us. And so you might be trying to kill off a bacteria for what, let's say, a
UTI.
bronchitis.
Okay,
So
bronchitis.
A lower, kind of like a lower, is that
Respiratory
lower? No,
tract?
that's upper. Is that upper or lower?
Bronchitis.
Yeah.
It's lower.
Is it?
Yeah.
Okay. So it's a lower respiratory infection. So you take an antibiotic for that, but that's not going to just target the bacteria causing the infection in your bronchioles, right? It's going to knock off bacteria in your gut, all sorts of places.
That's a good point.
And so there's going to be certain bacteria that will be sensitive to the antibiotic that will die off, but there's going to be some bacteria that will be resistant. Okay. And there is a possibility that these bacteria will then survive. And so now you'll be colonized, or at least if it's in your lower bowel, colonized. Like that.
Wait a sec. Nope. Go on.
By that particular bacteria type. Okay. Which then, if it's pathogenic, it can then induce its own type of pathology, right?
Yeah.
And this is where the thoughts, so you're changing your microbiome. And this is, what's the infection that's?
C. difficile.
C. difficile, yeah. So
Clostridium.
Clostridium, yeah. So
Yeah.
you get overrun
Yeah.
by certain bacteria that are now resistant to the antibiotic that you've just used.
Yeah.
Or maybe you've never used it. Maybe you've now, what's the word?
Been introduced to it for the first time.
You've got bacteria from someone else or some other place that's coming to you that is now resistant without ever exposed from your own body. And
do we have a cure for C. difficile?
Fecal transplants.
That's it.
So then you've got that in the individual like us, but you've also got the environment. So if we start to expose the environment, it's almost like the environment has its own microbiome. And if we expose the environment to all these antibiotics through certain things like the use in agriculture. So at least in America, 70% of antibiotics used, or it's not really prescribed, made, I guess, is used in agriculture. And so the animals are going to pee it out, and it's going to go into waterways and spread. And so you're going to have bacteria exposed to antibiotics that we were using for our own self that are now becoming resistant.
Wow. So when we look at avoiding antibiotic resistance, one, try not to use them in animals maybe.
It's going to be hard.
Yeah, true. But they use it in chickens just to get them big and buff.
Yeah, all of them. I think all livestock is used as a growth promoter.
Another one would be if you get given antibiotics by a healthcare professional, take the full dose or take it at least as they tell you to take it.
Don't flush them down the toilet.
Don't flush them down the toilet. Don't take old or leftover antibiotics.
Just on that point, this is you might find this interesting. Maybe you won't.
Probably not.
Because I live on.
I'm yet to be interested by anything you've stated.
Because I live on acreage, we have a septic tank, and we're not technically supposed to be like it's best to avoid using the toilet when you're using antibiotics because it knocks off all the bacteria in the septic tank that breaks down the feces.
Well, you know what? This is a good point. Everyone hears bacteria and they think bad. There are far more bacteria on this planet and around us that have no effect to us or a beneficial effect compared to the pathogenic bacteria. I think there's less than 100 pathogenic bacteria, but there's over 1,000 different kinds of bacteria that we can live quite happily with. And a lot of bacteria are it's not necessarily good versus bad. It's just got to do with where they live. So we've got bacteria living in certain parts of our body, which if they moved elsewhere would be bad.
Yeah.
Like E. coli, for example.
That's right. And that was my last point is if we try to kill bacteria and so forth off every surface that we live in, like using antibacterial wipes and sprays and everything, it can remove the whole abundance of all these bacteria in variety, and then only the nasty pathogenic ones dominate. And
if we had no bacteria on or in our body,
you would be fat.
We'd be dead within a year.
Don't you get fat?
So
what happens to the mice?
Yeah, so with some mice, they gave them antibiotics, and it had shown that over time they increased their adiposity and increased their likelihood in susceptible mice to get type 1 diabetes.
But the sterile mice ones,
yeah,
are they fat or skinny?
Fat.
Okay.
No, fat. Yes. So so some of the studies have shown that if you look at the gut microbiota, that the greater the variability, the better they are at metabolizing, and the fewer variability, so the less variable, the worse they are.
So you need to eat more?
I don't know.
This is where I always get confused. I always thought that the more bacteria, the better utilization of food.
So you get bigger.
Yeah.
I think it's the type of bacteria. I think it's a ratio between the Firmicutes and the Bacteroidetes. They're the two major types that live within our gut. And the ratio between those two, even though it's a very gross way of looking at it.
Sounds like Greek civilization.
Thank you. I'm Serbian, actually. That the ratio between those two can be an indication as to gut health. but we don't really know that yet. But we should do another episode on bacteria itself and maybe gut microbiota once more evidence
Have we
comes
already
out.
done that?
No, we haven't.
Okay.
We should. All right, we better go.
All right. Any final words?
Yeah, follow me on Instagram at Dr. Mike Todorovich. That's at DrMikeTodorovic. That's a long last name. You can follow me on Twitter at Mikey Todd, MICKEY. TOD. I always okay. Facebook, Dr. Matt, Dr. Mike's Medical Podcast, which I look after. Matt doesn't do anything. And on the YouTube page, we are uploading videos nearly every day now. So if you want new videos on anatomy, physiology, pathophysiology, pharmacology, log into our YouTube page. If you want to talk to Matt, well, send us an email at gubiosciences@gmail.com.
I've got Twitter.
Matt's got Twitter, but
I don't really use it.
It's pointless. Look, if you want to contact Matt, you got to go through. You got to go through me. See ya.
Thanks, Mike.
Bye.